So this is a review of Work Package 3, Serverless Computation for Big Data. My name is Gil Vernik. So we start with overview of the work package, and then we see the progress till mid-project. So this is the general structure of Cloud Button work packages, and we see here work package 3. There are 4 tasks, where 3 of them managed by IBM and 1 is managed by Atos. If we get into more details of this work package, then this is how those 4 tasks are organized. So we see task 3.4 is actually the one that's sort of on the front. It's the one that user can interact with this Cloud Button toolkit via UI or via notebooks. On the other hand, there might be some batch services, jobs that they also can integrate with Cloud Button toolkit. And this is task 3.4. Internally, it's responsible for all kind of operations like data partitioning, generate job descriptor, it does also pick up results and generate all kind of inputs and outputs for the users. Now, so this is what users basically see when they interact with Cloud Button. And internally, we have a Cloud Button core, and it actually tasks 3 other tasks, 3.1, 3.2, 3.3. They all sort of in the backend, and it contains the backend capabilities of Cloud Button Core, which is high performance fast engine, and it involves cache, some data sharing, of course, backend compute platforms, and storage. And we're now going to see all those in more details and the progress we had so far. So we start with task 3.4 because, as I said, it's the one that actually is more visible to the consumers of Cloud Button. So the task is about how to integrate applications and function as service engines, and by take care of all important aspects of fault tolerance, shuffle, caching, big data partitioning, and many more. We have good status updates, so we implemented Cloud Button Toolkit, as you will see now, and we demonstrated its capabilities, of course, both in Cloud Button, but we also showed how its benefit outside of Cloud Button for all kinds of use cases, which includes HPC, molecular dynamics, protein folding, multicolor simulations, and many other use cases. So Cloud Button Toolkit, just to avoid any confusion, so there was a Pyron prototype from Berkeley. It was designed for AWS. We initially we took this Pyron, we liked that project, and we extended it to work with IBM Cloud, so we called it Pyron IBM. It was just to take the Pyron and extend it to work with the IBM Cloud. Cloud Button Toolkit is based on Pyron IBM. But Cloud Button Toolkit has about 900 commits on top of Pyron IBM. It has completely different structure, completely redesigned. So it's a different project, and we also now want to rebrand it a little bit so it will be more clear. It has broad interest, it has good visibility, it has exploitation inside IBM Cloud, where it's used by different stakeholders, both internal and external to IBM. And the visibility of this project actually brings more contributions. It's an open source project, Apache license, and so we see contributions that come outside of Cloud Button Consortium. And some of them use this project to connect other big data frameworks to be serverless. So we see that we're sort of on the right path, and there's a good visibility and a good usage of this project. So in general, this is how an example of Python notebook, and you can just take Cloud Button toolkit and you just integrate it with the 2 simple lines of code, and then you just can invoke any of your functions and run it into the cloud. So this is clear Cloud Button experience where you just don't need to do anything. Just take your code, press this Cloud Button, and it's invoked there. So this MapReduce style API that we expose, not only, you will see them in a different work package where they present on APIs of Cloud Button, but here I just want to emphasize how it works. So again, you have your input data sets. It may be any data. You have your business logic, your function. Now you take Cloud Button Toolkit, you take its executor, and just run your function against your input data sets, and it's invoked and executed automatically in the cloud. Then you just take your results, and that's it. So it works not only for Python, it works actually, the business logic can execute any executable package. So this is how we managed to implement and demonstrate the usage of a Cloud Button Toolkit for a broad range of scenarios, like to run Gromax, Protomol, dlib, GDA, FFmpeg. So those are special packages, some of them molecular dynamics, some of them for image processing, video processing, and we can use exactly the same pattern where you just take your business logic, you let Cloud Button to deploy it and execute it in the cloud at the right scale. So we show some of the features of Cloud Button Toolkit. We can't talk about all of them in this presentation. We're limited in time, but the most important one is the big data partitioner. It's actually the core of any big data engine that need to deal with large amounts of data, because if you have large amounts of data, you need to figure out how to partition it correctly, so there will be parallel invocations, parallel executions, parallel data processing of these input data sets. So Cloud Button Toolkit, we support all kinds of input data sets that we know how to partition them correctly. It can be arrays, URLs, location into object storage. We know how to partition CSV files without break a line in the middle. And we also support custom-based partitioner, and this is exactly sort of what you already saw in the EMBL metabolomics use case, where we use this sort of custom data partitioner to partition their data sets based on some molecular similarities. So we have this job, and then Cloud Button, after we finish its analyze and partitioner finish to understand how to partition the data set, it generates a job descriptor with a clear JSON file, and it just provides it back to the Cloud Button core for further processing. So this is very clear and modular architecture, and that allows us more extensions in the future. So now we are going to see the more backend components and the task that deals with them. So we start with task 3.1, which is high performance stateful function as a service engine. Again, so this task is about how to make those serverless invocations are efficient. It contains a lot of things that we need to implement, and, for example, to also develop new techniques, how to make those invocations more efficient, in particular serialization, deserializations, and again, how to make this high-performance execution of those tasks inside the backend engine. So we developed many things so far. In particular, we know how to use Argo workflows to deploy serverless workflows. We developed capabilities to integrate InfiniSpan as a memory cache. We have advanced serializations. We use some data locality. And so let's see in more details the progress. So first of all, the idea here is to sort of containerize the model with serverless compute engine, because so with Cloud Button, you just take this user software stack and you deploy it into, it's wrapped into Cloud Button runtime inside those fast backend. And then this is what gives this great benefit for the applications to run there, because Cloud Button Toolkit provide them many capabilities like interactions with object storage, or it may know how to access partition data sets, monitor progress, and so on. So this is the high-level overview. And so first of all, we implemented all kinds of compute engines and any storage connectors. We are not limited. We can further implement many more. Currently, Cloud Button we support IBM Cloud Functions, Google Cloud Functions, Amazon Lambda, and we can easily extend it with more clouds. There's also hybrid use case supported, where we can deploy to different cloud providers or to different serverless architectures. And we can support any storage connectors, IBM Cloud Object Storage, Ceph, Google Storage, OpenStack Swift. We also support in-memory storage solutions like InfiniSpan. And again, the modularity of our implementation allows us to implement much more if we need it in the future. Now, temporary data, so any big data engine generates a lot of temporary data. This is true for Apache Spark, for Hadoop MapReduce, or any other engine you want to take. And efficiently dealing with temporary data is the core of efficient data processing, because sometimes this may be a bottleneck. So in Cloud Button, we see two types of temporary data. One that's Cloud Button engine generated, something internally that the user is not aware of. And on the other hand, user flows may also need to generate some temporary data, like shuffle between different stages. So we support pluggable storage options for any temporary data. We implemented InfiniSpan integration with Red Hat, and we will more continue to investigate the benefits of it. But so far we see that it greatly improves the traffic, because now we can use in-memory solutions to store temporary data instead of going to some object storage. Cloud Object is another implementation we implemented, how to share data between different stages of invocations, and we heavily use this in the metabolomics use case, since they have many stages, and this is how we share data between stages. Serverless pipeline, it's another addition that we added. So it allows us to create a pipeline of invocations that need to be performed in a specific order, and then we can make sure it's invoked in the serverless paradigm. So it has a lot of benefits for all kinds of scenarios, in particular for data scientists that need to share notebooks, or just to need to make sure their notebooks are efficient enough. And you can see more demo on this in different presentations. You will now see the link. And it's obvious that having serverless pipelines to be a first-class citizen Cloud Button, this is what makes this so unique, our approach. So before Cloud Button, it was a disaster. A user need to write its notebook, then he may need to call another user or send him email, I finished, now you can process data, and then maybe they need to also to perform all kind of tasks, and then those notebooks may be limited by network. So that's very complicated and very unfriendly. On the other hand, with Cloud Button, this is what we implemented. We now have serverless pipelines where they know how to process those notebooks. The user doesn't need to communicate one with another, because they just submitted those notebooks and they're executed in the cloud based on their priorities. And you can see here two links where you can see more videos and additional presentations on the serverless pipelines. We now go to task 3.2, Cloud Button Operation Support. So this task is important, because here we try to understand, okay, so we use serverless, but we want to make it efficient, we want to make it cost effective, because it's not a big deal to use serverless and pay a lot of money. You want to use serverless and also enjoy from reduced costs. And so this task is exactly deal with this effort, how to make this serverless not only effective solution, but also cost effective. And we developed all kinds of models here. I like to choose the right platform of executions, and we also do some improvements with serialization, deserialization, and we have good results here. So first of all, serialization, again, it's a known problem in big data frameworks, in any big data framework, that serialization may be overhead. And serialization, deserialization, those who are less aware of it. So it's a process of turning your data into bits. This is what we call serialization. Then those bits can be stored in storage or transferred over the network. Then there is another process that takes those bits and deserialize them into that initial object that was serialized. So this process is CPU consuming. It's also maybe some bottleneck in certain cases. So we developed all kind of pickle strategy and methods where we see in some certain cases it might be valuable to use Docker containers to store results and thus avoid serialization. And we also see when we can skip them in certain cases. Again, this is work in progress. We have initial good results, and this will greatly improves the overall experience. Another aspect that we have, and this is what we also experiment with in metabolomics use case, is cost-effective execution. So first of all, we try to see. It's not wise to use serverless with its maximal allowed usage of memory and compute because it's more expensive. So you need to figure out what kind of memory you need for this particular workload, so you will not get memory limitations, and on the other hand, it will be effective and you will pay less money for this. So choosing optimal memory in runtime, this is key for effective big data processing. This is how you reduce your costs. So in Cloud Button, we do some sampling and we estimate right memory based on sampling, and then we try to figure out what's the runtime we want to use. We demonstrated it for metabolomics use case, and we are going to generalize this model for broad scope. So those sampling are very important because it also prevents timeouts or all kinds of serverless limitations that exist. And we also use some other cool tricks, like we reuse authentication tokens, because if you have 1,000 invocations, and now each invocation needs to authenticate itself, it's a painful process. In Cloud Button, we use 1,000 invocations, but we only need to authenticate once, and then we reuse the same token across many invocations, and it's very effective. Hybrid model, this is what I said we also experience. So the hybrid model, it's where you want to leverage perhaps more legacy virtual machines plus serverless invocations. And we see trade-offs here very nice because it can improve overall performance and reduce costs. And the paper at Servermix about to be published, which is exactly address those novel aspects of hybrid use cases for serverless. Task 3.3, Instrumentation Quality of Service. So this task is led by Atos, and the idea here is to monitor and understand the efficiency of the system in runtime. And so there was a plugin for they developed plugin for Knative, and then data can be analyzed in runtime. Again, you can see more details in their presentation and in their video. So this is just an overview. So the extension here is for Knative backend, and then there is a plugin that just observed health of the pods inside Knative. Then it generates data, and it can be analyzed in Grafana. And then you have this Cloud Button quality of service metric selections, which is very important. And you can see more in their video on this work. Summary. So we so far have very good visibility of Cloud Button. Both, first of all, we demonstrated already use cases in Cloud Button, but it's also very visible outside because we managed to demonstrate HPC over serverless, molecular dynamics, Monte Carlo simulations, satellite data processing. Those are very important use cases. And we presented them on very good venues, in particular Strata Data in New York, where we presented how the easy move to serverless computing and how we can improve simplified data processing. We recently wrote a very nice blog with the metabolomics, with the MBL, on how we use our technologies to perform this big data processing, because their use case is really big data, and we managed to demonstrate it. So again, this blog contains everything from the story till actual code that people can experiment, and it has very good visibility on all social medias that we shared it. And we also presented in Stuttgart Meetup and many other venues that we presented. So that's it. And thank you very much. This is the thank you.